For the last talk of this morning session, well, actually for this day, because this afternoon we have an afternoon off. So it's my pleasure to welcome Max van Renesse, who will talk today about Brownian motion on Wasserstein spaces. Please, Max.
Use my own audio now. Is that okay? Okay. I can start now. Okay, so I would like to thank the organizers for the invitation to this meeting. It's a great privilege to be here. I should have come many years before. I recognize now, and I'm glad I finally made it. So thank you very much. It's a great privilege to be here among this distinguished group of colleagues. Okay, so I will talk about a slightly off mainstream subject, but which is my subject of passion over quite some years. It will be about the attempt to construct stochastic processes on the space of probability measures, which deserve or which have some properties which make them candidates for a Brownian motion on Wasserstein space. So as I just said, it's slightly off mainstream, and I decided to give this as a survey talk on some results of the past couple of years, because this is probably the best that I can contribute at this moment to this exciting meeting. Okay, and the outline of my talk is that I will start with a little bit of motivation, and then I will introduce the Dean-Kawasaki equation, which is an equation from statistical physics that comes about naturally in this context. And I will discuss something which is probably can be called a no-go theorem for the actual thing that I want to do. So I start basically with an assertion which suggests that what I wanted to do and what I want to do, have been wanting to do over the last 10 or 15 years, is basically impossible. However, this no-go theorem, we discovered this no-go theorem only recently. And if we had discovered it before, we would not have done all the work that we did before, which basically shows that the no-go theorem still allows for a little bit of an exit. And I would like to introduce you, I would like to present basically by pictures, a couple of these exits that we have found even before we knew about this no-go theorem. So that's the outline of my talk. So I start with motivation, no-go theorem, and then I'll tell you some workarounds around the no-go theorem, although this is not quite the historical order. So let's start with some motivation. Okay, I start with certain dynamical systems on the space of Wasserstein, on the Wasserstein space of probability measures, which is our preferred state space. We want to do analysis, data science, or even, as I shall try to do, on in probability. So let's start with this thing with a paper by Felix from, I guess, 2001, which was inspirational for many of us, I guess everyone in the room, where Felix introduced this formal Riemannian calculus with this Riemannian structure on the then to be interpreted tangent bundle of probability measures. And he showed in this paper that the quadratic Wasserstein distance can be interpreted as the intrinsic distance which comes with this formal Riemannian tensor structure. And also he gave another computation which showed that the gradient flow for the entropy can be quite easily understood as a gradient dynamics or gradient descent dynamics for the entropy function. Then basically at the same time, or I attribute this statement to Brownian, although it's more or less a folklore statement, and I would make this statement, or I would like to make this kind of a remark that I guess that many of the things that you discover your own in optimal transportation in some way or the other, it's not quite clear whether Jan Brownian already knew that or just didn't bother to write down. Anyway, so it's one of those statements that everybody knows, and Brownian probably knew already 200 years ago, that the geodesic equation on Wasserstein space basically corresponds to the compressible Euler equation. I'm saying this because this geodesics the geodesic equation on Wasserstein space, of course, is already a second order equation, which leaves the framework of this first order dynamical systems on Wasserstein space. So by this very elementary remark, you see that already looking at second order dynamical systems on Wasserstein space may be a beneficial thing. And then I myself, for my own enjoyment, basically made some computations which then appeared in 2012. Yesterday, Christian was nice enough to mention this. So I made some computations using this second order calculus on Wasserstein space, and I looked at now not geodesics, which would correspond to the case when you have 0 here on the right hand side. So this equation here, if you like, is the geodesic equation on Wasserstein space. And of course, the next step in when you do not want to consider geodesics alone, the next step is to look at equations of motion or Newtonian or Hamiltonian system. So this would be this equation that I write here would be just the blueprint equation for a Newton's law of motion, which says that acceleration of a curve on this Wasserstein space is given by a force, which is then given as the gradient of an energy function. So F here plays the role of an energy function. And so this is a Newton's law, which is induced from F. And if we choose F in this fashion, which is the entropy squared, or the Fisher information, the gradient of the entropy squared, which we also call the Fisher information. And if there's an additional potential specified in the system. So then if we solve this equation here, I mean, suppose we know what it actually means, and suppose we can solve this equation, then this equation actually, or this dynamical system of the trajectories can be mapped to give a solution to the Schrödinger equation. And the mapping that maps these solutions, so recall that this is now a second order equation. The boxed equation is a second order equation in our tangent bundle. So a state of the second order equation is actually a tangent vector. And so a tangent vector here, it consists of two pieces. It contains a base point mu, and it contains a velocity. So you can use these two components of this state of this second order ODE to define this now complex valued function, but just using this usual decomposition. And then you find function, which I have just introduced, actually does solve the Schrödinger equation. So, and the transformation also can be done in reverse fashion. So in that regard, solutions to the Schrödinger equation are in fact exactly solutions to this Newton's equation on Wasserstein space when you choose the potential function f in an appropriate fashion. And I would, so I would like to highlight, I mean, this is not the main point of my talk, but I just added this little slide to my talk today because it adds to the general theme of the workshop, and it adds to the idea that it makes sense to look at dynamical systems on Wasserstein space, not only for first order dynamical systems, but also second order dynamical system. And since I try to be a probabilist, the next step, of course, is very natural that I look at dynamical stochastic dynamical systems on Wasserstein space. Okay, so this is advertisement. This slide here is advertisement for second order dynamical systems on Wasserstein space. This was advertisement for first order dynamical systems on Wasserstein space. And the next slide will be advertisement for stochastic dynamical systems on Wasserstein space. Right, so again, so if, yes, so if you have, so this is a second order equation that I'm looking at. So the tangent vector is a mu dot. This is not a state. It's actually a dynamical description of the system at a certain moment. It comes with a certain mass distribution at motion. So in the dynamical part, the velocity vector field is a gradient of something in this autocalculus. And so I don't care about the constant of integration. I just use this S and plug it. Is that an answer to the question? Yes. And what you can also do, this Otto-Riemannian structure, every Riemannian manifold has a natural symplectic structure. You can work it out. You can work also the symplectic structure in the Otto case. You can just do a little bit of computation. It's a straightforward thing. And then you can, and then you can analyze the role that this mapping actually plays. And you can find that this conversion of this state mu, or mu dot to be precise, into this wave function is actually a symplectic morphism between the different symplectic structures. People in quantum mechanics don't overstretch the fact that the Schrödinger equation in its wave function representation is a Hamiltonian system. It can be understood as a Hamiltonian, classic, so to say, Hamiltonian system using the complex structure of wave functions. And this thing here, this map here, which we call Madelung transform, is effectively modulo one codimension, so to say, is a symplectic isomorphism. So therefore, these two descriptions of the Schrödinger equation are totally equivalent from a dynamical system point of view. So that emphasizes this point. And finally, again, this is not actually the subject of my talk, but since it was mentioned yesterday, I put a little bit of emphasis on it. Finally, I would like to highlight the point, which is probably known for everyone who understands the reason or the meaning of the Schrödinger. This complex number here is in this representation is an artifact or is just a consequence of this choice of coordinates. There is no complex time. So in this representation here, in the Newton's time representation, there is just no complex time. It's not there. It's just a choice of coordinates which brings up complex time. Okay, so that was advertisement for second order dynamical systems on Wasserstein space. And people who worked actually on the rigorous mathematics of this, I think the most active researcher in this field is Wilfried Gangbo, who did some substantial work on these dynamical systems. But these computations are formal, and it's a challenging thing to do this on a totally sound mathematical rigorous basis. And then finally, Christian also mentioned it, just to conclude this slide properly. Christian mentioned yesterday something that I learned from Giovanni Conforti when he was with me as a postdoc. So if you replace here, and Christian emphasized this enough yesterday, if you replace this plus by a minus here, and you write down what it actually means, this ODE here, or second order ODE, this is the displacement interpolation for the Schrödinger problem. So the Schrödinger problem and the Schrödinger equation in this representation just distinguish one another from putting a plus or a minus. But this is actually not the subject of my talk. The subject of my talk is about advertisement for dynamical systems on Wasserstein space. So what I want to study and what I'm doing since 15 years or something is trying to introduce models which can serve as Brownian motion on Wasserstein space. So it's a Brownian motion on a Riemannian manifold, but in this case on an infinite dimensional Riemannian manifold. And that would be basically a natural thing to look at, right? Because it would be natural fluctuations of a system which has which is a conserved mass, but which performs random motion according to the energy which is invested by dissipation. So if you think about this physical interpretation of optimal transportation, it says that redistribution of mass follows statistics governed by energy dissipation. Okay, just for those who are not so familiar with Brownian motion on Riemannian manifolds, here's this one little slide. So if you have your preferred Brownian motion on a manifold, your preferred Riemannian manifold or metric space even, then you can, in order to have an idea of what a Brownian motion on this space is, you can just start what is called a geodesic random walk or a metric random walk, which is just a piecewise constant Markov chain, basically, which selects uniformly in spheres of the current point, the target point, and then does the jump. This has a radius, of course, and then you can do hydrodynamic scaling. You scale the radius, make it smaller and smaller by 1/k, and you speed up time in a quadratic fashion. Then you can do a then on good metric spaces, you can argue that this is a sequence of processes which are compact. And then the limiting process will be something like this. And this is then your candidate of a Brownian motion. So you see what you need on a naive basis, you need only a metric, so to say, to start the procedure. That's why I emphasize that it's good metric. Okay, to be honest, that's one of the difficulties. You don't need only a metric, but you also need a uniform distribution on bolts, which is of course in infinite dimensions a difficult thing, basically impossible thing. But nevertheless, it gives you some idea. And this corresponding diffusion process that you constructed, it will still exhibit the metric in a quite natural fashion, because if you look at the heat kernel that comes with this diffusion process in an exponential scaling or in short time asymptotics, it exhibits exactly the distance of your metric space. So whatever kind of stochastic process on a manifold is given to you, if someone says this is a Brownian motion on this space, the first thing to check whether this Brownian motion is actually really related to the geometry of the space is this short-term asymptotics, because this is essentially saying that the large deviations rate functional for this process, so the small-time asymptotics, are exactly given by this metric structure of the underlying space. So, and what we would like to do is we would like to discuss several processes on mass distributions which satisfy this basic requirement. Okay, again, so that's my motivation. What if we now choose as our metric space the Wasserstein space of probability measures? Can we construct such a process? Can you tell me what is my finishing time? I see. Okay. 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 Thank you. Okay, and now I'm still in the motivation part. So there are various ways to construct Brownian motions on Riemannian manifolds. One is this Markov chain field central limit theorem, but you can also use charts and solve stochastic differential equations and then put the thing back. So that is the approach of constructing a Brownian motion with an SDE on a manifold. Here we have an infinite dimensional manifold, so we need to be ready to deal with stochastic partial differential equations because we are doing SDEs in infinite dimensions. And if you think about this SPDE approach a little, and you think about what is the actual covariance matrix, so that features the right Riemannian structure, then you would necessarily come up with such a noise term on the right-hand side. So I'm changing gear now at this moment. I'm talking about stochastic partial differential equations, since we will basically be guided to some extent by this stochastic partial differential equation representation. So you will see in one slide why this choice of multiplicative noise. Okay, probably I should take one step back. So if we don't have this, so in some sense, what I'm doing at this moment, I'm looking at an equation which is like this, which is a B of xt. Sorry, I'm doing this for all those who are not so familiar with stochastic differential equations. So this is your familiar notation of a stochastic differential equation in finite dimensions, but now the symbol x gets replaced by mu, and delta mu is a gradient operator. Here B is a gradient vector field, so the gradient operator here is the Laplacian. It's just the tangential gradient operator on Wasserstein space, and the sigma of x of t, it's a transformation of this of the characteristic statistics of the noise, will be this interesting x-dependent tensor, which is applied onto a white noise field. So that's the logic of this equation as a stochastic partial differential equation. And if you write down a Riemannian Brownian motion in charts, you will of course see this Riemannian tensor encoded in the sigma, if you want to have the right noise structure. And here the sigma is this strange transformation of the noise. You will see in a second why it is natural. And this Laplacian in front I write because it's the best kind of regularizing tangential object that can help you to deal with this irregular noise. Was there a square root? No, it's absolutely important it's a square root. So if you let me, I'm sorry? It's really a square root, yeah. So let me write this in a different fashion. I'm multiplying by square root of mu, which means that I write what? I write this as a mu times 1 over square root of mu dwt. And this would tell me that I'm having basically a continuity equation, which is driven by a random field, But the random field is scaled in such a way that it scales the actual total fluctuations of the random field are locally scaled in an inverse proportional way by the actual density of the system. So, yes, absolutely, exactly, absolutely correct. So this would be basically, if this guy is, let me say it again, if this guy is replaced by some fixed velocity, by some fixed field psi, this would be just transport in a random by a random vector field. But here we scale let me say it again, we scale the noise characteristics of this random vector field in such a way that we have a characteristic scaling of mass versus fluctuation. That's important for this Otto interpretation, or for this Otto Riemannian perspective. It is just exactly the right type of scaling, as you shall see in a moment. Okay, so when you think about a natural SPDE description of such a Brownian motion, I claim that if you think about for a while, you will arrive at this equation inevitably. And then several years later, I was told by a colleague that this equation actually has a name in physics, and it's called the Dean-Kawasaki equation. And it's it's one of the standard equations to describe, or it's one of the standard equations in statistical field theory, so to say. So it describes what people call non-equilibrium hydrodynamic fluctuations, and it appears in as a candidate description of so-called mesoscopic systems. So if you have a microscopic system and you do a large n limit, like a hydrodynamic limit, then you there's some intermediate scaling regimes that these are the type of arguments that you find in these papers, such that you already see a hydrodynamic large scale behavior, but there's fluctuations around, and this equation here is supposed to describe that. So there are other models or other derivations of this equation in physics. Okay, so that would be the number one equation that we would like to solve. It is called the Dean-Kawasaki equation. And that will be, in a way, our starting point and our guidance in this field. Okay, now comes a few rigorous results, which I will only probably most of the time motivate and will not give too many details about. So here's the no-go result about the Dean-Kawasaki equation, which is the most recent one in this context from us, and which is interesting probably for some of the people who work in particular in SPDE theory. So first of all, we need to make a definition of what we understand by a solution. This stochastic partial differential equation is really bad. There has been a lot of development in stochastic partial differential equations over the last couple of years, which was triggered by the works of Martin Heyer in regularity structures and Massimiliano Gubinelli with this paracontrolled calculus. But this equation is supercritical with respect to this renormalization theory. So we will now show that this equation is really ill-posed, which is not in contrast to the existing recent theory. And one first step in the analysis of such equations would be to come up with a proper definition of a solution. And should probably mention that there is a familiar class of SPDE, which is also famous in measure-valued SPDE processes, which would probably read like this: plus square root of mu dw. So if you don't write the divergence, but just write it like this, where now W is a scalar random field, then this equation is called, or this SPDE describes super Brownian motion, which is a standard model in measure-valued processes. So that's super Brownian motion. SPDE, or sometimes it's called Dosen-Watanabe process. And you see that there's there's a certain similarity here between the two SPDEs. So the difference between the very well-established model of super Brownian motion and this Dean-Kawasaki equation is just this innocent divergence operator, which you put on top. But there is a solution concept for super Brownian motion, which is very effective, and we just copy this in this case. So we say that we have a solution to this Dean-Kawasaki equation if, for all smooth test functions, where's an F for all F? For all test functions which are compactly supported, say, if we test the measure-valued process and subtract a bounded variation part, which is obtained by mapping the Laplacian, the drift operator, onto the test function, we want that this is a martingale, which is in a way the replacement of saying that this is constant over time in case we had a deterministic equation. In this case, the new process would be just a deterministic solution to the heat equation. But now we don't ask that this is constant. We want that this is just a martingale, and the quadratic variation process of this martingale needs to have this structure. That's our concept of a solution for the Dean-Kawasaki equation. And as you might expect, or as you might guess from the structure of the noise, It's exactly the same concept of a Martingale solution that is used for super Brownian motion, except that for super Brownian motion, you don't have the gradient here. It's just the f squared. And here, the difference between super Brownian motion and Dean-Kawasaki is just this gradient in the function. Yeah? And yes, and what I also would like to say that this term here, of course, is exactly the term that you expect from the autocalculus. It's exactly the Carré-Duchamp that you would like to see. Basically, what you specify here is the Carré-Duchamp operator, or the second order coefficient, the second order jet guy, so to say. That's exactly the second order jet for this stochastic process, which you want to see if you want to see this auto energy on the tangential energy. So that this is this grad f and mu squared comes exactly from this structure here. So the divergence, you dualize it, you put it on the grad on the f, that gives you the gradient on the f, and then you have the square root, and you have the white noise, so therefore you just contract to the diagonal. So therefore the grad mu, the square root of mu becomes a mu, and the grad of f is squared. So that's why after an integration by parts and doing the expectation, you see exactly this energy for the fluctuations. It's exactly the right Carré-Duchamp. And now comes the no-go result, which says, okay, so this solution here, and by the way, beta here is a drift parameter, right? It just, the Laplacian here is just diffusion. So it's just the usual thermal diffusion, which you add to the system. So that you have two levels of activity, if you like. So you have basically a system, that's the model here. You have a system which performs heat flow, but then it is in a bath, in some sort of a heat bath, and the heat bath pushes the substance around according to these fluctuations. That's this Dean-Kawasaki equation. And so then you have, since you have two levels of, in this theory, you have two levels of activity. You have one degree of freedom, say, which measures actually the thermal diffusivity of the substance alone. And depending on the scaling, then you have normalized to be one, you have a certain thermal diffusivity of the exterior substrate, so to say. And now comes the interesting theorem here. Say this in the sense of the solution that we have just defined, this equation has a solution if and only if beta is essentially integer value. And in this case, the solution is given as just the empirical distribution of independent Brownian motions. So it says that the Dean-Kawasaki equation makes sense as just a field theoretic description of independent Brownian motions, but you have to tune the parameters correctly to actually match the field, the random field, if you like, that you obtain when you do any independent Brownian motions. And except that if you don't scale the parameters like this, then there is no solution. This is a remarkable rigidity of this equation. And for instance, if we go back to the super Brownian motion, this thing here is a reasonable and rich model for a continuum of beta parameters, and you can solve it completely. But this equation here has a tremendous rigidity with respect to the parameter beta. So solutions exist only if beta is integer, even. The rest of the talk will certainly be very non-technical, so therefore I give you two lines of proof for this result here that we obtained some while ago. It's just two things. First of all, you write down, there's a nice log Laplace duality for this particular equation. So if you assume you have a solution, then you can do a little bit of E2 formula, and you can write down exactly the log Laplace transform of this equation. This log Laplace transform is something that people like to do in measure valued processes anyway. And here you get a very explicit log Laplace equation, which is basically solved by a nonlinear, or just by the Hamilton-Jacobi semigroup again. In other words, you can compute moments and expectations of the system very, very nicely and explicitly, just using a Hamilton-Jacobi equation. And the second lemma is just a lemma about non-negative random variables. And it says that if you have a non-negative random variable and you introduce this probability generating function, and if this non-negative random variable has a probability generating function which is smooth at the origin, then this random variable must necessarily be integer value, almost surely. It's just two very small lemmas. If you put them together, you you combine statements, you arrive at this in remarkable rigidity. Okay, so what does this say? This says that our candidate SPDE for the Dean-Kawasaki, or the candidate SPDE for this Brownian motion of Wasserstein space does not exist, or it's just something trivial because it's just independent Brownian motions. But of course, we have some positive examples where we can modify the equation a little bit in order to obtain interesting models. And now I'm coming back to something that I did long time ago. It's one of the three types of models that we have that basically does something like a job. I'm now in one dimension. I want to do Brownian motion on Wasserstein space, which on probability measures in one dimension. And I'm not quite sure at this point. I have to take a break probably, and I need to make a decision now which model I shall present to you. Okay, let me go by pictures for most of the time, and then one model I shall present with a little bit more care, because some of this you might have seen already. So the point is that the Dean-Kawasaki equation in a way becomes trivial because we have not the right type of correlation in the system. So all these models that I shall present at this in the next few minutes, all these models are trying to introduce correlation into the system such that you can somehow evade the dichotomy between law of large number and central limit theorem. What we see here, probably that's a worthwhile remark. Let's go back to the Dean-Kawasaki equation, although it's probably not so interesting after this result. This Dean-Kawasaki equation is an equation which is supposed to interpolate between law of large numbers, which is this guy, and in a way central limit theorem, which is the diffusive behavior. So when we talk about the mesoscopic system, it's somehow a system which we would locate somewhere in between those two scaling extremes, law of large numbers and fluctuations. And so if that is supposed to come from a particle model, you need to come up with a particle model where you scale the correlation in the system in such a way that if you do a large n limit, you obtain a system which has a hydrodynamic behavior and fluctuations at the same time. It's not so easy to come up with systems that do not follow this typical dichotomy of law of large numbers and hydrodynamic and fluctuations. And here is one such a system that we found long time ago. So this is a system which describes an anharmonic chain. So here it would be basically, say, in these simulations, which are also old, you could think of, here we show trajectories of 4 different particles. Here, this is time. This is time, and this is space. This is, or the unit interval. And effectively, this motion is confined to be the unit interval. And what we see here is the motion of 4 particles which move in the unit interval. They are mainly driven by Brownian motion, but then each of these guys has a neighbor to the left and a neighbor to the right. And we have an electrostatic attraction, depending on, so if beta is small, this is positively negative. So we have an electrostatic attraction of each of the particles to its right or left neighbor. Beta is a strength parameter of this, and here you see that there's some scaling with regards to the number of particles. And depending on the strength of this attraction, we can observe different models. And what we find here, for instance, when we have beta very small, so I should probably say beta is counteracting this attraction. We see that this mutual attraction of the processes generates a picture such that these particles actually like to stay together, and the bulk of the particles will reduce its speed. So under this effect, the particles will form clusters. And if you look at a cluster from far away, you see a bigger cluster which has less diffusivity, which is exactly the thing that we would like to observe in this scaling of diffusivity versus mass. And we showed a long time ago that you can do in hydrodynamic scaling of this particle system. So you replace now, you pass to the measure value description of this system. And if you pass to this, then it's possible to pass to a limit and to identify a limiting dynamics of this system, which is, now this is rigorous here. Of course, it needs to be interpreted, but it's a rigorous statement, which is our Dean-Kawasaki equation with general beta, but with a singular additional normalization in the drift. So there's a strange singular distribution which you have to insert into the system in order to get an interesting, non-trivial dynamics in the end. Okay, that's one of our models. And we have done some work a long time ago with Theo Sturm about this, about the invariant measure. And there is what we call the entropic measure, which is the invariant measure for the system, which is not a big surprise because the entropy plays a dominant role for the heat equation part in the system, which is, as we all know, the gradient dynamics. So this would be the natural invariant measure for this dynamics. Then we have for this system, we have exactly this short-term asymptotics that we would like to see. It has exactly this large deviations properties in terms of the heat kernel, which brings up the quadratic Wasserstein distance as we want. And this made us very happy, but the model is very non-local in terms of its construction. And now I have, let's say now I have 4 or 5 minutes left, and I will really go only by pictures. A more recent version of this idea that particles can come together, form larger particles, and then slow down in their diffusivity is what we call the modified Arasia flow. The Arasia flow is a standard model in the study of chaotic systems. It's a system of Brownian motions which start from everywhere in the continuum. And then once 2 Brownian particles meet, they just move together. That's the Arasia flow. It's a model of, if you like, balls in a chaotic fluid, which can stick together. And we just devised a modified version of this Arasia flow, which says that if particles come together, then they carry along mass, then the scaling, and also the diffusivity after they come together is scaled down. So what you see here is, if you like, you can guess, or you can, with a little bit of goodwill, you can see that this simulation actually gives exactly this feature. You have 3 particles, say each of them has mass 1/10, and then they form a particle here of mass 3/10. And the 3/10 is the inverse diffusivity now of the particle that continues. The mathematical description of this Arasia flow follows a little bit this idea of Kunita flows. This is the kind of a theory in which you would want to work to describe this. So you describe the system as a field of martingales, which is indexed by the continuum, and you specify basically the correlation structure of this martingales. And with this correlation field, with this field of martingales, we can then pass to the corresponding push forward measure. So we have now if you like, a chaotic dynamical system, and we can study the effect of this chaotic dynamical system when we carry mass along with this dynamical system. This is then a stochastic process in the space of probability measures. And we can see that this system, which is constructed in a very different fashion as the one we started with, this system, or this stochastic process, again solves a version of the Dean-Kawasaki equation. So we have a very different system, but given the same SPDE. And here this Laplacian operator, the star should be here. The Laplacian operator that is here is not quite a Laplacian operator. It's the Laplacian, if you like, of the support of the measure, which is again a singular thing. But I would like to stress that if you don't work with particles which carry different masses, you don't basically see a difference between this nonlinear Laplace operator and the linear operator. So this is a version, or this is a brother of the Laplacian, which looks like quite the Laplacian if you don't pay attention to it, and if your system is simple. And it might have been overlooked, I don't know, by some people who do with this, that you have to deal with this kind of Laplace. And now finally, I will skip more of the mathematics. And now our most recent model, remember this was meant as an advertisement talk, so therefore I don't expect you to go into the details. So this is our most recent version of this modified Arasia flow. We have now a reversible version of this modified Arrhenius flow split, which has now a splitting component. Again, the construction is very different. And what we see here is a simulation of this model. So here you could think of, yeah, let me spend 2 more minutes just on this picture, and then I probably finish. So what we see here in this simulation is a version of this, or is a simulation of this new model which we came up with. It is a measure-valued system, an infinite dimensional measure-valued system. And if you look, and the red trajectory is the center of mass of the system. And the center of mass of this system is a Brownian motion. So in a way, you could think of this as being just a Brownian motion. It's just the trajectory of a Brownian motion that starts at the origin at time equals 0. But then we allow for this Brownian motion to immediately decompose into a continuum of smaller particles of various sizes. Each of these particles performs a Brownian motion, but this Brownian motion of the individual particle is again scaled inverse proportional to its mass. And then these particles, they can just split off, and then they can come together again, form a bigger particle, stay for a while, slow down their diffusivity, and then break up again. This is a modified Arrhenius flow with splitting. And if you look into the simulation of these trajectories, I'm not sure if it's really convincing on this, but here color code is for weight. So let me just try to isolate something. Yeah, so here you can see, here you have such an event. When you have, if you like, a bigger particle, then which is relatively slow, if you like, or not so diffusing, not so widely. So you have a dark trajectory, which is a particle of relatively huge weight, which is diffusing relatively slowly in comparison to what is going afterwards. And then here you have a breakup event. And then this particle breaks up into smaller guys, which then diffuse with a higher diffusivity. And so this is a system which is pulsating as a diffusing, this is a system which is a pulsating, coalescing, fragmentating system, which is an honest infinite dimensional measure valued process. Its center of mass is like a Brownian trajectory, but a level below, you have something quite exciting going on. And again, this is a process. Let me just skip over to the main characteristics. Again, this is a process which is an honest measure-valued stochastic process. It assumes values in the space of probability measures because the total mass of the system does not change, and it has the right large deviations result, which means that the statistics or the fluctuations of the systems are again governed by a quadratic Wasserstein distance. So therefore, this is another candidate for a Brownian motion on the space of probability measures. So let me go back to this picture, which I like quite a lot. This is a one-dimensional process on the space of probability measures. This could be an interesting candidate as a model of some substance or of a fluid which moves in a completely random fashion, but whose statistics, local fluctuation statistics, are really governed by the Wasserstein distance. So that's what it should be. Thank you for your attention.
Thank you, Max. Can I just ask you to mute for the... Thank you. Let me turn this back on. Some questions, perhaps? Yeah, Christian.
Thank you. So in your last example, again, we have a discrete support, finite support, yes. And is it? Do you think do you have any candidate for a diffusion on Wasserstein space, or is it really unavoidable to have this discrete structure coming up?
Yes, so yes, it is. I wish I had a model which would not be discrete. Although the discreteness of this model here is already a more complicated discreteness than just a simple one, because there's a continuum of ways how this thing pulsates. So it's quite complex, discrete, so to say. Right. This equation here, if you look at this equation, in a way, it has no Laplacian operator. There's no smoothing in this system. And in the model that we did with Theo many years ago, where the entropy comes in, where we really have this Laplacian still, there we have measures which are really a Cantor type, which are continuous but not absolutely continuous. Right. So, but they are not atomic. And this is because in this model, if you like, we have the smoothing, still a smoothing operator, which is also inserted into the system. So in a way, it's quite correct, and I'm thankful for this question. In a way, what we did in the last couple of years was basically to try to understand or try to give stochastic processes which are driven by this dynamics alone, and when this guy is not present. And therefore, we would not accept, we are ready to accept that something non-smooth is coming out. So in a sense, we were not kind of looking at it. Yes, but it's probably not the final word on your question.
Well, actually, I can ask you we have a question from Enrique last. Do you have such kind of buffering model in larger?
No, at this moment, the analysis and also the construction of these models is confined to a one-dimensional state space, unfortunately. I should mention that there is works, of course, we are not the only people who looked into such problems. There is work by Lorenzo dello Schiavo, who has a multi-dimensional interesting diffusion process, but in his situation, the particles don't interact at all, and so the discrete structure does not change over time. So when the particles should meet and so forth, we are still confined to a one-dimensional situation if we want to have this interesting, really singular interaction. More questions? There's the chat. There's some activity in the chat. I'm not sure.
Yeah, there's a delay.
Oh yeah. Okay.
We have a question here.
So you have a result of converge mu to the capital N converges to mu. That's a
this chain, this unhomogeneous chain model.
yes. Oh, next page. Yes, here. So this is this a mean field limit, or what's a capital N? It's a
No, it's not a mean field limit because this is not a Dean-Kawasaki situation because we have only years average. And so we don't get a law of large numbers. This model is meant to, okay, I don't know, it's a mean field limit, but this is beyond the conventional mean field limit. We have a system which has so strong correlations also on the large scale that even in the hydrodynamic limit, we really have an honest stochastic dynamic.
okay. Oh, okay.
There's no average, this is too much correlation for averaging.
Okay.
But this is beyond. So in the mean field limit, my understanding is always you have a Dean-Kawasaki thing, and then you get this deterministic hydrodynamic equation, right? This interaction.
Yes.
That's not the case.
Okay. So the capital N here is
Number of particles. It's a large N. It's a large.
okay. This N is not same with little n in your you have a theorem for the solution of the equation, right?
No, that's a different N. That's
Different. Okay.
Model.
Okay. Thank you.
So I think it's time to close the session for this morning, and let's thank Max again. And sorry, one more question or announcement. I don't know.
Not a question.
It's announced. Okay, so let's say bye to the internet, and we will see you tomorrow morning at 9:30. Bye. Yep.